This has been the day of everything not quite working right. So let's get back to our class. You guys are section 13. Blackboard going to work for me now? Oh, it is. There's nothing special here except I want to check on something real quick. So you don't have lab 4 points. So the lab you're going to do today, you obviously can't upload it right now because there's no place to put it. That will resolve itself probably during your lab. It's 4.1 actually. So even though Python starts counting 0, Dr. Cleveland has trouble inserting a number between 4 and 5 without breaking his otherwise fancy scheme of organizing things. So today we're going to talk about 4.1.
You asking for a refund?
Well, you're getting a book for free. I mean, other classes you got to pay $100 for this kind of garbage, and here you're getting the garbage for nothing. So today we're going to look at data structures, in particular 3 kinds of great value: lists, tuples, and dictionaries. They're funny sounding words. I don't know the origin of the words. I'm not going to sweat it. And then arrays. And then we'll just make a comment. Later on we'll be using NumPy, which is an external package that you load into your kernel. And you will forget that the arrays package even exists at that point. Not because it's better, but because it manages a lot of it for you. For the time being, we will do it properly. So our objectives for today are for you to have an awareness of data structures available in Python to store and manipulate data. We're going to implement lists, arrays, dictionaries, and tuples, and we'll repeat almost everything that we do here in lab. And then address the contents of said critters, lists, dictionaries, and tuples. So the elements of computational thinking, for which data structures and to a lesser extent conditional statements are part of, are decomposition, abstraction, and algorithms. The decomposition portion is the data interpretation. Abstraction is taking a collection of things that we somehow want to be related. So everybody in this room has a name. So we could all live together in a list for this room, and the contents of that list could be each of our names, and that would be an appropriate data structure. So when we want to refer to an individual, we go to the, what room is this, 214? Oh, this is the CCAT room, because if you stay here too long, you'll see cats that don't exist. So if we go to the CCAT room, let's see, who can see their number? Who knows what number they're sitting behind? CCAT room index number 2 is you. CCAT room index number 3 is you. We've got a bunch of invisible people, and then we have number 10, number 11, number 20, and that would be, the data structure would be called a list, and we refer to individuals on the list based on the number that's in front of you. And who didn't even know they had a number in front of them? Oh, good. So at least you pay attention when you walk. So what is a data structure? They are a specialized means of organizing and storing data in computers in such a way that presumably we can operate on them more efficiently. So the alternative of having CCAT room with the different indices would be to refer to us as individuals, and that would make any sort of structural organization quite a bit more complicated because you'd have to be kept track of all the time. I guess we could just air tag ourselves and let Apple take care of it for us. So in the world of data structures, the relatively common ones are lists, tuples, sets, and dictionaries, as pictured up here in the picture. And in the olden days, there was another arrow there that went to arrays somewhere over here. I was instructed to remove that because that wasn't a true data structure because it used a separate package. But if you want to be really precise, there should be an array over here as another data structure. It is another data structure. It's just not in primitive Python. So we'll start with a list. A list is a collection of data that are somehow related. So how are all of us related, at least for the next 40 minutes? We are all in the CCAT room. And if you see a cat in this room, I know where we can see a cat. Let's go ahead and see a cat in the CCAT room. There's a cat. Now how do I get my stupid screen back? Slide out. There you go. So a list is a collection of stuff that's somehow related. And we have a convenient way, therefore, to refer to a collection of similar things by a single name, CCAT room, and then by using an index. So CCAT room 34 is, who is CCAT room 34? This guy next to you. It's you.
Is it me?
You are.
64 is behind me.
You're CCAT 34. Go ahead and look at the number in front of you. Oh, 30. I can't.
Yes, see, it's 30. That's what I thought. Because I know for a fact I'm not 34.
Okay. So that.
34,
Yeah, 34 is an invisible. So one of our invisible classmates. The Institute of Invisibility would be pleased to know how many of their members are sitting in class with us at the same time. Damn, multiverses do that to you all the time. So let's consider the math-like variable x that's up on the screen. Back in math classes, or at least algebra and that calculus stuff, subscripted variables were just a thing. There was nothing unusual about it. So we have a variable there. Its name is x, and it has subscript 0. There's another x that has subscript 1, x subscript 2, and so on, all the way, in this case, up to n. The value of x subscript 0 is, yeah, it's the numeral 7, and the value of x subscript 1 is 11. If you put those two together, you have the equivalent of a Circle K, but west of Texas in other states. And then you say, oh, thank heavens for 7-Eleven. So the variable name is x. The subscripts correspond to different values. So thus the value of x associated with subscript 3 in this case happens to be 9. A visual representation of that relationship is displayed in my picture here, where we have cells. So you can think of cells as memory locations. They're like this big in my computer, and 18 months from now they'll be this big. So I was trying to get smaller by a factor of 2. It doesn't take very much to store a 5-volt charge or a 0-volt charge in terms of space. So this box, which has the name 0, so the name of the box is 0, so it's like one of the seats here with the number in front of it, contains the value 7. The seats in this room, which have numbers in front of them, contain the value of each of you. So your seats are far more valuable than anything in a Rascally Rabbit computer. Position 1 contains an 11, index 1 contains an 11, index 2 is a 5, 9, 13, and so on. So the name in this example is my list. The index are the positional indicators, and then the contents are the actual value. That's a list. So we can refer to the list by its name, and we have an example already laid out here, and I think I should have. So there is the example lifted right out of the notebook. Make sure I'm on the right computer. Okay, so I can screw that one up with no damage to anything. So if we type the keyword mylist, then the equal sign, open square bracket, 7, 11, 5, 9, blah, 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 close square bracket, and execute it. Sure enough, nothing happens. And that's because we have been asked for output. And if we look at the contents of my list, lo and behold, we get 7, 11, 5, 9, 13, 66, 99, and 223 back. Enclosed in square brackets, delimited or separated by, what's that symbol that's between each of the numbers? A comma. So it's actually given us a visual clue to what kind of object that is. Square brackets tells us it's a list. We can look at an individual member of the list by referring to its positional indicator and enclosing that in the square brackets. So the syntax of that statement right there is go into the object named myList, which is my list. Find the contents of my list that corresponds to position ID 7, which happens to be the 8th thing in the list because our friend Python counts at 0. So 1, 2, 3, 4, 5, 6, 7, 8. It's 223. And when we execute the script, lo and behold, we get a 223 back. So we know there's only 8 things in the list. Excuse me, yeah, 8 things, 0 to 7. So if we try to query the non-existent 9th thing, we will get that error message, and that's fairly common. That'll happen a lot if you're just learning this stuff. So list index out of range, what that means is that my list, we're trying to address something that doesn't exist. Now if you are expecting there to be 9 things and there aren't, you may have made a mistake somewhere else that created that situation. If we put a colon, I think it'll go to the last thing. A colon lists the entire list. There are some other special characters that you can get the first thing, the last thing, without having to know what its actual numerical index is. Let's not do that because that would destroy it. We'll just get the 0 thing, which is a 7. We also can create other lists, and so this next one is called my other list, and it is an empty list. It has nothing in it. That is not as stupid as it sounds. We use nothing lists to create memory space to put stuff into because our scripting language has the lovely added bonus feature that it won't be able to add to stuff that doesn't exist yet. As someone who is having trouble getting their treasure map to work found out, if the thing hasn't been defined yet, you can't add stuff to it, you can't query it. So here's my other list, and let's demonstrate that. Let's take my other list, which, did I restart the kernel on this? Yeah, I think I did. I know I did on somebody's machine. My other list right now I don't think exists, so I think I should get a pink box of, oh, I guess my other list does exist. We'll do it. Do you want to destroy everything? Yes, I do. My list. Okay, so my list 0 has the contents of a 7. My other list 0 should not exist. It won't tell us what's in my list 0 because this is a sloppy way of getting output and it'll only show the last thing. And we get this error, and the error message is my other list is not defined. It probably should have said not yet defined because we're going to go fix that problem. Let's go ahead and create our other list, which is empty. And now if we do that, it says my other list, the error now has changed from the list is not defined to the index is out of range. In this instance, position 0 has nothing in it because we've assigned nothing to the list. We can append to my other list some value, and so that first append statement will take the number 32 and put it into my other list and put it in position 0. And then the second one will take the 14 and put it into my other list, and that'll go into position 1. So we'll do that. Now if we go back up here, what should be in my other list position 0? The 32. Sure enough it is. If we look at the entire my other list, it's 32 and 14. So the result of those two append statements. And the commented statement here is another way to wipe the contents of a notebook without having to restart the kernel. And it's a useful tool, but I don't dwell on it very much because I kind of don't want you to do it. So we've just gone over the append method. Arrays are a special type of list that, unlike ordinary lists, so all we put in our list was numbers, 32 and 14, but we could have put strings into it. We could have put 32, cat, dog, Fred, and we could have put an element in our other list, which is actually another list. So lists can contain lists. You can have lists of lists. But arrays are lists that are by default all one type of data. So they're all integers or all floats or all double precision floats or all, these are the different kinds of critters that can live in an array. And some of these are outside the scope of this class. Signed and unsigned characters, signed and unsigned integers, and so forth. So signing means it can take positive and negative values. Unsigned means it's just positive value. We can have regular floats and double floats. So if you're really thirsty, you order a double float. Otherwise, you just get a regular float. And these numbers on the end are the smallest size of thing that particular array can represent. So for example, all floats are at least 4 bytes, that'd be a word size of 32 bits. And I don't know how many numbers you can represent with that, but it's a bunch. Whereas double precision float are 8 bytes, which are 64 bits, which is twice as much as 32. Give or take a bit. So that's the main difference between an ordinary list and an array. An array will usually, but not always, usually be numeric, and it'll either be a float or an integer of varying minimum sizes. So to create arrays, we have to use the array package, which goes by the cryptic name of array. It installs ordinarily with a regular Python install, so the package should be available to you. You still have to use the keyword import because by design, when you first fire up your Python kernel, it's a minimal kernel. The philosophy of this stuff is we make every load package as small as possible, and you add in features as needed. It's a complete contrary approach to the old Microsoft way of doing things, which is put everything that there is, even stuff that hasn't been invented yet, and then you have to actively disable stuff. So it's the difference between hacker-enabled and hacker-agnostic architecture design. And I can't comment on which is better. I guess everything all thrown in the bucket at the beginning is a lot better if you don't need to get into the depths of things, because stuff will usually just work. But having to add features means you can keep stuff very small and run fast. So if we import an array, to create an array, we use the array function, which has the word array as its function. And then we have this prefix array dot. And what that is trying to indicate is from the package named array, use the array function that's part of the package, and we're now going to create an integer array, and then we'll go ahead and provide a list of the contents, and now my array is our integer array. And then we can access the array the same way. The attractiveness of arrays is you're forcing everything numerical, and so it helps prevent mistakes. There are other ways to do the import using aliasing. So for example, here we have import array as R. And so now to create an array, we would type my array equals R dot array, the integer character, and then the array listing. As you copy, cite, modify, and run other people's code that you get off the mighty internet, you'll encounter the package named pandas and the package named NumPy, among the many other ones. You'll probably get them off a blog post because that's the easiest way to steal working stuff from other people. Incorporate working stuff from other people. Normally what you'll see is they will import NumPy as NP, and then all the NumPy features will be NP dot, whatever the method is. And if it's pandas, they will be import pandas as PD, and then you will access them as PD dot, whatever the method is. So if you see that, and I'll probably use it too, although I try in the stuff I'm presenting to you all to do it the long-winded way, because I think that's just more correct when we're learning, is to be very don't take too many shortcuts. We got to take some, or we'll never get done. So aliasing is gonna figure a big way in your near future. And so here we've aliased my array. Here I've done it as import array as R, which is not as fun to say as R. AR, and then you have AR array. We type the array. Ooh, I didn't. Let's go ahead and do it correctly. It works better that way. And if you send something to the type function and it comes back as array.array, it's telling you that it's an array. If we type a particular element in the array, it tells us that the contents of my array happen to be integers. If we add a 64 to it, and we get the length of my array, let's get the seventh thing out of it. So what index will the seventh thing have? Trick question, but not that much of a trick. I want the last thing in the array, which is either position 6 or 7, right? I'm going to guess a 6. It should come back as a 64, and it does. If I put a 7 in there, we should get the square of loser. And as I want to see what happens when we do that. We should be able to send the length in the argument, and it's supposed to be smart enough to know. But it's not.
It's out of range. If the length of the thing was 6, then it probably would have, but yeah.
There we go. So you can automate various interrogations, and that's on purpose. You want to be able to automate stuff so that the machine does all the work, and you get to sit there and enjoy your mint julep on a beach in some place that's not as cold as Lubbock is right now.
You really like mint juleps.
Huh?
You really like mint juleps.
Actually, I hate them. You ever had one?
No.
Don't bother. It's shaved ice and bourbon, and they stick a piece of mint in top, and apparently that's like a cool drink at horse racing. Now, horse races last, what, 40 seconds? Maybe a minute? So I get the whiskey and the ice part, because by the end of the race you want to be hammered, right? You don't have much time, so short of mainlining the alcohol, you've got to do something. But it's just fun to say, mint julep. What's your guys' favorite adult beverage? We can go Mai Tais in Tahiti, which would be better than being out there.
I like a
Manhattan?
Light Russian.
Black Russian?
White Russian.
Light Russian. That's cream and...
Kahlua, cream, and vodka.
That sounds pretty good. Okay. So now that you've all shared your drug and alcohol violation,
I'm of age.
well, there was some email that came through from the president about that, and I saw that, and I've been teaching for 35 years, give or take. I kind of ignore those, but basic drug and alcohol policy is don't mention it, and if you get caught, we'll throw you out or something. So you just tend to ignore it. I mean, I'm smart enough for you. Don't come to work hammered. That's stupid. You guys, you are our work, so you can come here as hungover as you want. There's nothing I'm going to do about it. If you do come really hungover and you have to puke, get it into the trash bin, because this is a carpet floor. There's nothing worse. And if you're next to somebody who's losing it, it's polite to hold their hair so they don't get it in their hair. Some of you are grinning, oh, so you've been there. That was a drug and alcohol policy. Let's get back to work. We're going to talk about tuples. Employee locator devices are horrible. A tuple is a special kind of list. And it's a list where the values cannot be changed after the list is created. That property is called immutability, or you can't change the contents, which would be a smarter way to do it, but then it wouldn't sound so cool. So we call it immutable. It's useful for list-like things that are static. That's one use of it. The more important part, I'll highlight it for you. Most of your packages and functions that you either write yourself or you incorporate from the internet produce output. They tend to be tuples. The output tends to be tuples. So if you have to find a particular element in it, it will work better for you if you know that that's a tuple that you're addressing. Here's an example of a tuple called my tuple name, an extremely stupid name for a collection of the months of the year. I imagine there are 12 items in that, unless I missed one. Once a tuple is created, we can't remove elements of that tuple. It's not possible. It's by design, you can't change the contents. We can destroy the entire thing. That's easy, because we are humans and we're really good at that. But we can't destroy individual parts of the thing. So that surgical precision they all talk about in destroying stuff, yeah, BS. But we can create new tuples out of pieces of other tuples. So here is a very contrived, admittedly stupid example to show how to do that. Let's say we have a tuple called a tuple. It contains the contents A and B, the letter A and the letter B. If we print a tuple, what it will give back to us is the tuple representation. It tells us that there's an A in position 0 and a B in position 1. See what I mean by stupid example? Big whoop, okay? Let's suppose we want to take a value C, and we're going to name it added value, and we're going to create a tuple called added value tuple, and it's going to contain the added value and then a comma. Notice that I call that a dangling comma. There's a comma and then the end result of the tuple. So we have implicitly created a tuple that kind of has some empty space in it. And then we'll repeat that with another tuple called the short tuple, and that is comprised of a tuple, position 1, which has value B, and then another dangling comma. And now if we add the two tuples together, so short tuple plus added value tuple, and we're going to put that result into our new tuple. The contents of new tuple are going to be whatever's in short tuple, which happens to be a B, concatenated with whatever's in added value tuple, which happens to be a C. And then when we print that tuple back, we'll get B and C, the two tuple items. Along the way, we're going to destroy the original A tuple and print the new tuple. So we've just taken A and B and converted it to B and C. That's admittedly a long-winded way to do something that should be simple, but because of the undestroyability of individual tuples, we would be forced into a method like this. When we learn about functions, we could put all that in a function, so we don't have to keep remembering to write all this.
So why would you stack tuples?
I don't have a good answer for that off the top of my head. The only reason I can imagine having to do something like this is you're getting one tuple out of some function, cosine, sine, hyperbolic cosine. You're getting another tuple out of some different function. You want to put them together because you want to plot them. Our next special list is the mighty dictionary. This is a list where the items are related in data pairs. In each pair, there's a key, and there's the actual data. So dictionaries are created using the curly bracket or the dictionary constructor method. So with curly brackets, so here's one called My Pet's Names and Mass. Open curly bracket. Our first dictionary item is right there. The key happens to be Dusty, and then after the colon is Dusty's value, which is 7.8. Next one is Aspen, 6.3. Next is Marimy, 0.03. Alternatively, we can use the dictionary constructor method. If you're typing stuff, that's probably easier because you don't have to keep track of quotes. And we're assigning to the key named Dusty. Those look like variable assignments to me. So dictionary is a collection of named variables that have something assigned to them. So Dusty 7.8, Aspen 6.3, Marimy 0.03. And those two dictionaries are functionally identical. They're not the same object, but if we look at them element by element, they're going to be identical. Dictionaries' properties are that they're in no particular order. Dusty and Aspen could be interchanged upon creation, and we still access the correct key. The elements are changeable, so we can change the contents of Dusty, Aspen, Marimy, but we can't change those names. We can add names and remove names from a dictionary, but we can't change the names. So we can use the add remove as a sneaky way to change a name. Here's some examples, and I'll just go ahead and copy it and actually execute the script. See if I've already done that. Looks like I didn't already done that. So we're going to create the two dictionaries, and then we're going to print the contents of each one, and we'll discover that they're identical. And sure enough, that printout is as close to identical as I can imagine our computer could be, because it is character by character identical on the two lines. Okay, big whoop. How do we access the contents of a dictionary? We access it by the keys, and we can enclose a key name in brackets. So somebody pick one of the three names. What are you feeling frisky about? If you don't do it, I'll do Aspen because it starts with the letter A, which is the first letter of the alphabet. And so it's now returning that the contents in the dictionary associated with the key Aspen is 6.3, and so on. So notice that was a square bracket. There's another method, which is get, and let me see if I can remember how to do the syntax. I think you go by key name. So My Pet's Name and Mass get Aspen recovers the contents of Aspen. The get method also lets us, access it with positional values, although I don't think it's going to be very interesting. So Aspen's position 1. It'll work better if I'm in the right. I wonder what it just did. I did not get the pink screen of stupidity. Oh, there is no positional thing. I'm using get incorrectly. Fortunately, that's in the notes coming up, so I'll be able to get it correctly. Oh, I just made a joke there. Our next type of special list is a set. So sets are used to store elements of different data types. Sets have the property that they're in no particular order. So sets, for all practical purposes, cannot be indexed. So if you go set position 7, it doesn't know what that means. The elements of a set can be changed, and non-repetition is enforced, which means that you don't have two identical elements in a set. Sets are enclosed in curly brackets, and that was done by the creators to make our lives miserable, because sets and dictionaries seem to be created almost the same way, and in many instances they look the same. Sets cannot be nested, whereas dictionaries can, and we can create sets with different data types. Let's look at a couple of examples. So here's a set called mySet, and we've set the set up with a key 1 that corresponds to the string 1, a key 2 that corresponds to the string 2, a key 3 that corresponds to the set 1, 2, and 7 of 9. And then when we interrogate the type of my set, it tells us it's a dictionary. So there's a dictionary using the natural numbers as a key, and here's how we use the get function. So let's go ahead and create the set. Let's set up the set, huh? So there's our set. We just created a set, and now we can use the get function. I'm just going to arbitrarily put a 1 in. And so what it's going to do is it's going to go to the key number 1, and it should return ONE, or pink screen of death. Good, it did the way I thought it would. Now if we pick index number 3, what it's going to return is this other dictionary, if you will. So 1, 2, and 7 of 9. And then if we use get again, make sure I get my syntax correct. Okay, so what's inside the first circular brackets is this script right here. And now we're going to run the get method again, and we're going to get whatever corresponds to the number 3, which in this case will be 7 of 9, and that's how next generation was created. Except I didn't tell it what to get, did I? That's how you will be assimilated. So that's the get method applied to dictionaries. And continuing on with our story, now we'll look at an example of a set. So sets have no explicit keys, or another way, a way that works for my brain is that the set contents and the set key are the same thing. So for that example of my set, 1, 2, and 77, my set contains 3 keys. Happens to be the numeral 1, the numeral 2, and the numeral 77. If we get each of those keys, we'll return the contents of the set. We will test that conjecture the hard way, live, not Memorex. Pretty sure that the get method works with sets. So we have a choice there. We can enter a 1, a 2, or a 77. Which would you all like? What's your favorite letter of the alphabet today? 1, 2, or 77?
77.
77. Why is it a letter of the alphabet? Oh, okay, because it's an intercept. Okay.
And we get this object. The set object has no attribute of get, so let's try a direct access to its key. It's not subscriptable. Okay, so I'm a total loser today, and that's what the red box of loserness is. Here's another set, and I'm going to skip down here and see how to access members of sets. me go back to my notes. Maybe it's sets cannot be indexed. Okay, so we can't get it that way. Elements can be altered. They're unique. Continuing on, and I will look up how to access a single element of a set, because that obviously is doable. If we have two sets, so we'll have our first set is my set, 1, 2, 77. Our second set is your set, Apple, Cat, Rock, 77, Sunset Strip. Those two sets have only one element in common. What's the common element? We'll go back to set theory that you had in calculus. The only thing that appears in both those sets is the numeral 77. Keep that in mind. We have union and intersection functions available for sets. The union is indicated with the pipe symbol, vertical line. On mine, it's the key that's just above the any key on the right side of the keyboard, just below delete, and it's shift. Go ahead and do it over here. It's that shift vertical thing. It's called a pipe, because I guess you could smoke it. The intersection symbol is the ampersand, like the and sign. So if we do my set, pipe, your set, what that does is it's going to join the two sets into a third set that only contains the unique items of both sets. So one of the 77s is dropped. You can think of it as that way. You can't have 77 twice because you can't have two identical items. The intersection is only going to find the common element, which in this case is 77. And so when we run that expression, we get the union is 1, 2, Rock, 77, Cat, Sunset Strip, Apple. And the intersection is 77. We also can use something called a set constructor method, which is the keyword set. And then on the outer part of the keyword, you're doing a circular bracket. On the inner part of the keyword, you have the tuple that is the set. Or just think of the double round bracket for a set constructor. And we create this set, which is apple, banana, and cherry. There's a logical question, what's the difference between a set and a dictionary? I've got a couple of explanations incorporated from the mighty internet. The first one is kind of useful. The second one is an example of something you're all going to become very familiar with if you have not already, called a useless definition. You're in college now, so you need to get used to those. Talking in other people's sleep is what we do. So the second definition is not terribly useful for anyone wanting to actually know what the difference is. But the first one is useful. A set's like a dictionary where the keys themselves are the values. The keys are unique, duplicates are not allowed. And you can build sets with duplicates, and the constructor by default drops the duplicates. So you can try that with the first set above if you want. And in both cases, we can create empty versions of each of the structures. We can create an empty dictionary simply by giving the dictionary a name and assigning it empty curly brackets, and that is an empty dictionary. And we can create an empty set by using the set constructor function and putting aside it empty circle brackets, and we have an empty set. And both those have utility in some instances for sets and dictionaries. There's some more reading here if you want. I would certainly recommend the sets tutorial and maybe the arrays tutorial, but the sets tutorial would be really helpful. You also can go back to what's supposedly our official textbook here and try to work your way through that. And we're now ready to start lab 4.1, and so I will see you in 9 minutes. Thank you for your attention and not falling asleep. Try not to freeze to death. stop the recorder.
I know you have to